Welcome back to Introduction to Computational Fluid Dynamics. I'm Professor Steve Miller. Today we'll be talking about the most basic formulations of the boundary conditions for computational fluid dynamics. And these might apply especially for the Navier-Stokes equations, LES simulation, RAND simulations, Euler equations, these types of equations which we talked about previously. In the previous class, we introduced the concepts of boundary conditions. We talked about their basics, what boundary conditions are and what types they are, applied to simplified ODEs and partial differential equations. In this class, we'll talk about a number of boundary conditions. These include the wall conditions that are slip and no slip, where velocity can move across a wall or it's stationary, the so-called wall functions to try and reduce computational expense, the free stream condition, which minimizes farfield disturbances, general far inlet and outlet conditions, including the Riemann invariant conditions, which are very robust. We'll also talk about the so-called absorbing layers, the symmetry condition, and a few other miscellaneous things. Let's get started. The first boundary condition we'll talk about today are those corresponding to walls, that is, solid surfaces within on the edge of the domain. The first one, and perhaps one that's most commonly used in computational fluid dynamics, is the no-slip or viscous wall. They are essentially used and said interchangeably. For example, someone might say viscous wall or no-slip wall. They mean the same thing. It's just what we might have in most natural and physical or engineering flows. It corresponds to a solid wall, and it's one of the most simple ones to implement and understand in a CFD code and apply in a code if you're running it. It's simply setting that the velocity at the wall is zero. For example, in 2 dimensions, you might write u equal v equals 0. The velocity is 0. This may not be enough to fully specify the conditions, especially in a flow which is compressible. For example, a heat flux might be set, and a direct condition for the so-called heat flux might be Q at the wall is equal to some heat conduction coefficient times the derivative, the normal derivative usually, of the static temperature in the normal direction of the wall. We can also set the static temperature at the wall directly. This would be, of course, an isothermal condition. Now, there are some situations where the wall boundary conditions might break down, and we'll talk about those in a second. On the right of the figure, we show one simple case. It could just be a domain where we have a cylinder and crossflow. We've seen these natural visualizations and simulation results already in this class. We would be simply setting the no-slip or wall condition at the cylinder surface. Everywhere on that surface, we would also specify that the velocities are 0 and that perhaps the heat flux is 0 or the temperature is some value. Or perhaps we have some heat transfer rate, which we can explicitly set also within the boundary condition by setting the left-hand side of the equation in the lower left-hand corner of your page to a constant and solving for perhaps t with the system of equations. Here the flow moves from left to right. The contours represent velocity magnitude. The left side is an inlet boundary condition. The right is an outlet boundary condition. The top part of the wall and bottom part of the wall are where we're setting the velocities equal to 0. You can see within the domain the fluid is relatively undisturbed and moving in the right direction at a relatively constant rate. Now, at the walls, you can see that there's this dark blue color, and you can see in the color legend on the right that that corresponds to a velocity magnitude of 0. So indeed, the velocity or the no-slip boundary conditions have been enforced and we're finding the right velocity. This is probably an incompressible simulation, and so there's no need to set the temperature heat transfer rates. Now you can see that as the flow moves to left to right in this very, very coarse domain, there's not much entrainment of the flow. This is truly a laminar flow, it's steady, and unfortunately there's not enough grid points or resolution to let the boundary layer grow. It's a very coarse domain, so even though we have a solution, it's probably not one that corresponds to some physical reality. You'll also notice in the upper left-hand corner that truly, the velocity is not 0. So on this particular grid, they set the grid points at the wall, but not in the corner as the no-slip condition. They've left this upper left grid point and the lower right grid point as essentially an inlet condition, letting the flow to come into the domain. Now, in some solvers, it can cause a huge problem to have a velocity inlet condition, like on the left, and a no-slip wall in adjoining parts of the domain. Sometimes this might crash the solver. We'll talk about a way to get around that next. The next boundary condition we'll look at is the so-called slip wall or inviscid wall. Excuse me, this title should be inviscid, not viscous. Viscous would mean no slip. Now these types of walls are where we only limit the flux through the wall to be 0, or the velocity through the wall to be 0, and we allow the velocity to be non-zero tangential to the wall. That doesn't mean that the velocity can sometimes, just through the natural solution, become 0 at the wall, but we're just not enforcing it. For example, a stagnation flow with a slip wall boundary condition could have velocities that are 0. The magnitude of velocity is 0 at one point on the wall where the stagnation point is. But this is very much an edge case. Generally, the velocity at the wall will have a non-zero component tangential to the wall. How do we enforce this boundary condition in the continuum form of the equations? We would simply write that the velocity wall with the inner product of normal to the wall is simply 0, and that's the only condition we're applying. We can also, if it's a compressible flow, we would have to add the additional condition that about the temperature at the wall or the heat transfer rate through the wall. These have to be set too. For example, we might have an adiabatic or isothermal wall. These would be set through this boundary condition down here, and I've already explained the nomenclature. You might ask yourself, when would we want to use a slip wall? Where do they occur? Well, it's very simple. In nature, if we let helium and the temperature of the helium become very, very small, the viscous effects of the fluid become negligible and go to 0. In this case, the inviscid fluid would require a slip boundary condition because the viscous effects require that the velocity at the wall be 0. This is a more complicated subject in physical reasoning, which I'm hoping was explained to you in previous classes or will be explained to you in a graduate class. If you're really curious, you can dig deeper online. Now, if we're solving the Navier-Stokes equations, we can still, of course, use the slip and viscous boundary condition. It is applying something which is typically unphysical, but it might help us find a numerical solution. For example, in the previous example, it might have been better to put part of the wall as a no-slip wall, so we do not find numerical problems and instabilities where the no-slip wall meets the inlet velocity condition. If we're solving the Euler equations, it is appropriate to always use a slip wall. This is because of the lack of viscosity, and that does not mean that the Euler equations do not support a no-slip wall. For example, if you use the Euler equations in a solver, meaning the viscosity is 0, and you add in a no-slip wall, and you have very high-speed flows, then you simply would be approximating a high Reynolds number flow to some degree, although this is not typically done anymore. Let's look at one example of a CFD solution with slip wall boundary conditions. Here we see a two-dimensional flow, and there's velocity vectors shown. Each velocity vector has the same length, so its magnitude is colored by the color bar at the bottom, velocity in meters per second. It's normalized by the maximum velocity, which is now 1 in the non-dimensional format here. Now you can see internal to the domain that there's some kind of swirl or large laminar vortex formed. And in the middle of the vortex, it has very low speed, and the outer part of the vortex is very high speed by the red vectors up here. You can see also that in this domain, along the edges, the velocity vectors are indeed tangential to the wall. So we can see that this particular case is modeling some kind of swirl where the velocity vectors have a slip condition at the wall. Now, resolving the turbulent boundary layer requires many grid points near the wall, and it's very computationally expensive to resolve, both in a steady and unsteady sense for the CFD solvers. Now, because such a large number of grid points must be placed near the wall, and their only purpose is to resolve the boundary layer, perhaps we can model the effect of turbulence near the boundary layer. After all, boundary layer turbulence and laminar boundary layers in all kinds of situations are one of the most studied traditionally and contemporary flows. We know a lot about it. Now, It could be that using this knowledge, we try and form a simplified model of the fluid dynamic equations and their behavior for the purposes of a boundary layer. This is where the so-called wall functions come in. A wall function would replace the traditional fluid dynamics model and boundary conditions near the wall by modeling a simplified set of equations of the so-called Navier-Stokes equations and Rand's turbulence closure. So we would ask ourselves, why not use less grid points near the boundary to model the so-called turbulence statistics? This is the true purpose of wall functions, to capture the effects of the turbulent boundary layer while using much less computational power. You might say to yourself, well, why don't I just use a lot more grid points? Well, you may not be able to afford to. So people in practical applications have turned and developed the so-called wall functions for laminar regions and turbulent regions. The laminar implementation of the wall function is much simpler. The turbulent one, of course, is much more complicated. Now we can imagine that instead of saying the wall shear stress goes as tau W equals mu partial u partial y for a very simple boundary layer, it might go as something like mu with some velocity at some point far away from the wall, say yp distance from the wall, which is much larger than what you would typically resolve, divided by the distance from the wall to a particular grid point, yp. So we replace that partial derivative with a simple approximation of its slope. Traditionally, there's something called the inner coordinates or wall coordinates of turbulent boundary layers. This is nothing but a non-dimensionalization of the y-coordinate of the turbulent boundary layer. We might call this term y sup plus, or the y plus distance, or y plus. Here we would approximate that simply as we did in the continuum form, but replaced with delta yp. So here, don't worry too much about this for now. We'll talk about turbulent boundary layers later again in the class. And if you want to go forward, you can look ahead or find something online to read. Here, y plus will be the non-dimensional distance to the wall, which is basically a function of course, something about the solution. Now, near the wall, the effect of the turbulent boundary layer, laminar boundary layer, is to create a force. And so we might also approximate that force as the negative shear stress at the wall with the area of the cell at the wall. This would, of course, be equal to something about the wall shear stress replaced with our earlier model times the area. And so we come up with this simple equation. Now, these can be replaced in the equations of motion with very great care to simplify the flow. Let's look at this in the particular turbulent region. Let's just look at the equations so you can understand what's being replaced and what's being done. Now, if the y plus value is greater than about 12, and we are in a turbulent region of the flow, then we would have to use a turbulent region wall functions. These are much more complicated. And in this particular table here, I have copied and shown the equivalent equations for the turbulent case. So you can see if your flow is laminar or turbulent, you would have to use two different models, and you would have to know which one to select in advance. This is very troubling because, of course, in certain flows, your boundary layer might transition from a laminar boundary layer to transitional to fully turbulent. So you'll have great difficulty in selecting a single model. Certainly, there's even more complicated wall function models which you can use. Let's look briefly at these types of equations. In the momentum equation that's tangential to the wall, you have something that's very similar to the laminar boundary layer, except now we have more empirical coefficients and scaling powers. For example, k to the 1/2 power, that's the square root of k. And here k is the turbulent kinetic energy at some point p from the wall. There's a momentum equation, which of course is normal to the wall. That would be the y direction Cartesian coordinates for a wall, which is in the y equals 0 plane. You would still set, of course, the normal velocity to 0. Then there's other equations. The turbulent kinetic energy equation would be simplified. The dissipation rate equation. We have not talked about these equations yet in the class, and we'll talk about them in turbulence modeling, but they too are reduced here. By reducing and simplifying those equations, we are simplifying the mathematics and therefore reducing the computational expense of the computer. We're also imposing some trends in the computational solution that correspond to physical solutions. This is where the power of theoretical fluid dynamics comes in, and that we can reduce the very complicated set of equations to something simpler for the computational solvers, and therefore find great cost savings. Finally, there's of course the temperature or energy equation simplification. And that, once again, is something to do with the heat flux or temperature within the boundary layer, actually, not necessarily at the wall. You'll notice subscripts here are P for the point away from the wall. Then we actually impose a formula solution, and the formula solution will go as u plus, which is like a non-dimensional velocity, will go as 1 over a constant, which is the von Karman constant, 0.41 typically, times the normal logarithm of something to do with the y plus distance, the distance away from the wall. This is a basic type of log law in the boundary layer. It's called the law of the wall, and we're focusing and applying that turbulence in boundary layers. Almost all turbulent boundary layers that we know of have this particular form in nature. And so we are forcing our CFD solution to correspond to the collapse and similarity of the solutions we find in nature. It's a very powerful thing. Now, the wonderful thing about this, of course, is that it will save us great computational expense. And typically, you would set the y plus distance in your boundary layer to be approximately 1 or 2. Now the first grid point is on an order of a factor of 10. So you're getting a factor of 10 coarsening of your grid in the boundary layer on just a rough estimate for these types of cases. Let's turn our attention to something called the so-called decomposition of the equations and the corresponding eigenvalues. Earlier in the class, we talked about the method of characteristics and how characteristic waves can be found and correspond to different types of particular eigenvalues. This corresponds to the so-called wave equation. Now, in a fluid or domain in 3 dimensions, if there's a disturbance in a flow of uniform velocity or Mach number, then information will travel upstream and downstream. Typically, in a 3-dimensional flow, there'll be so-called 5 eigenvalues. And this is no surprise because, of course, there's 5 major equations in motion in the compressible flow. These eigenvalues are positive or negative depending on the Mach number of the flow. We'll show these results in a second, but first I want to explain the physical connection. If I am able to disturb the flow at a constant Mach number, the Mach number could be 0.5 or 1 or 2 or any positive value, that's the scalar, then some waves will travel upstream or downstream, and another particular type of waves will travel upstream or downstream. And it all depends on the particular Mach number. These waves in particular are 2 sets of acoustic waves traveling at the velocity plus the speed of sound and the velocity minus the speed of sound. There's also 3 types of so-called hydrodynamic waves. These are typically the vorticity and entropy and pressure type waves. So let's look at a table of all the possible combinations and talk about the different particular wave speeds. Here's a table of the flow conditions at a particular boundary, or within the domain. It really doesn't matter for this case for the eigenvalues. At the boundary, of course, the velocities will matter. Now, for example, if we have a flow where the Mach number is less than 1, then you can see we'll have one eigenvalue, lambda 1, less than 0, one greater than 0, another greater than 0, another greater than 0, and finally, the last eigenvalue will be greater than 0. What does this mean? If we're in a subsonic flow and we make a disturbance, only one acoustic wave from that disturbance will travel upstream. The other acoustic wave will travel downstream. Information, that is the acoustic waves, is traveling in all directions. And then all other disturbances will essentially travel downstream. This is what happens physically. Now, you can do an experiment. You can go to a stream and look down, and perhaps you can see the bottom. You can see ripples and waves in the stream. Take your finger or take a little rock and throw it in the stream. You'll see that one wave, the surface wave, travels upstream, and another part of the surface wave travels downstream. The rest of the disturbances, say the turbulence created by the rock going into the water, or pressures, or vorticity, or any other type of structure, all travel downstream. So these eigenvalues of the subsonic problem are very physical and have an analog, of course, in the surface flow problem. This is the same thing that happens in a 3-dimensional Navier-Stokes flow. Now, for example, say we're in a supersonic flow. If you were able to go and make a disturbance in a supersonic stream, all the disturbances would go downstream. There'd be 2 acoustic waves going downstream in the direction of the flow, that is, at u, the velocity plus the speed of sound, and u minus c, the velocity minus the speed of sound. So you can see you'll create two acoustic waves traveling at two different speeds in one direction in a supersonic flow. Yet again, all other variables travel in the same direction. So what does this mean for specifying information on boundary conditions? For these particular cases, there's of course an inlet and outlet boundary condition. An inlet boundary condition is a boundary condition in CFD where the flow enters the domain. An outlet boundary condition in CFD is one where flow exits the domain. So let's consider the subsonic inflow condition first. If we're at an inflow condition where flow enters the CFD domain and the flow is subsonic, that means one acoustic wave is traveling out of the domain in the upstream direction, or the direction out of the inflow boundary condition. And then one acoustic wave and all the other values are traveling into the computational domain. The opposite happens in the subsonic outflow. 4 eigenvalues indicate that flow is moving out of the domain and one acoustic wave or disturbance is traveling into the domain. The supersonic conditions are much simpler, and that is true in the case that they're much simpler to implement. We'll talk about the implications and implementation of these boundary conditions in a second. A supersonic inflow boundary condition means that the flow is entering the domain at Mach number greater than 1, and therefore all disturbances are going into the domain. A supersonic flow which is exiting the domain at a supersonic outflow where Mach number is greater than 1, moving out of the domain, means all information is leaving the domain. On the right column of this wonderful little table, it shows what conditions one might specify. You'll notice the number of conditions, that is, variables or something about the variable, like derivatives perhaps, must be specified. So for the subsonic inflow, where basically 4 types of information are entering the domain based on an eigenvalue analysis of the Navier-Stokes equations, we would have to specify 4 variables. Here we might specify the total pressure, total temperature, and their particular angles. That is, we're setting the velocities. And you would, of course, have to specify some other information. As subsonic outflow, you only have to specify 1 variable, and that would be the static pressure. That's the famous subsonic outflow static pressure condition, which is available in almost all CFD solvers. For supersonic flow, it's very simple. Since in one case, all the eigenvalues are positive, corresponding to the inflow condition, and the other case, where they're all negative, you would either get to specify the entire solution at the boundary, like a direct boundary condition, or you can specify none of the solutions, where you would essentially extrapolate the flow from the interior grid points or volumes to the boundary. No information would enter the computational domain, that is, no disturbances like waves of any type or inflow at a supersonic outflow condition. It's impossible because information only goes downstream. You can see these types of things more so in our compressible flow classes. Let's take a minute and try and specify the velocities at an inlet and outlet condition. Typically, we would specify a magnitude and direction of the velocity in an inlet or outlet. These are the so-called velocity conditions. We are specifying the velocities. These are very popular boundary conditions for incompressible solvers. They are more ill-posed for compressible solvers because the velocities are not allowed to vary much. And that if a wave goes through the boundary condition, certainly there's a change in the velocities. So for a subsonic inlet boundary condition, it is very difficult to implement properly and hold the velocity exactly correctly in a compressible simulation. Incompressible flows and codes, of course, use this much more effectively. If we're holding the velocity, that is, it's specified the user at the boundary, then remember we have not specified other variables according to the eigenvalue chart just shown. So the pressure would be obtained by extrapolation from some internal domain. That is, we're letting the pressure vary at the boundary. We can't control it with this boundary condition. We can only control the velocities. We would also specify the inlet or outlet static temperature if we so desire. In compressible codes, the most popular inlet and outlet boundary conditions are the so-called stagnation conditions. And this is most heavily used in the stagnation inlet. It's very rare to have a stagnation outlet condition, unless perhaps you're in a supersonic flow at the exit of your domain. At the inlet, the stagnation conditions are critical, and many students and new people to CFD are a little bit disturbed to them because they would much prefer to set a velocity directly. In this case, if you have a particular velocity that you care about or want to maybe have at the inlet, you would actually use that velocity to find the corresponding thermodynamic conditions. In this case, we might say, hey, I have a velocity I want to have, and I'll be able to find some basically total temperature and static temperature at the boundaries. How does this work in practice? The total temperature or total pressure, or stagnation temperature and stagnation pressure, stagnation and total values are equivalent, is set at the boundary. The total temperature or total pressure is the temperature or pressure if you take a fluid moving and bring it to rest isentropically. These are really understood to you, explained to you in perhaps your introduction to fluid dynamics and compressible type flow classes and hopefully aerodynamics, and it's shown in the lab. This is essentially what you're finding with a pitot probe, a stagnation probe. That is, you're finding the total or stagnation pressures. Here at the boundaries, we are specifying those total values, the pressure and temperature, and holding them constant. We are letting all other variables change. For example, we're letting the velocities change, the densities, the pressures, and the temperatures. That is the static values of them. This is very common, and we'll be using this both in our homework problems and, of course, throughout the class. Let's look at one wonderful example of the power of the inlet stagnation condition for compressible flows. Here, the flow moves from left to right. And we have a domain. You can see this is actually a three-dimensional domain which is cut away of a conic type nozzle. The flow moves from left to right from a region of high pressure and temperature to the exit of the nozzle. Now, the contours are represented by velocity magnitude. You can see at the stagnation inlet, the velocity is very, very small. It's not actually zero because there has to be mass flow rate. It's just the contour levels. So there is some small velocity at the left. Anyway, at the center line, the velocity moves along and accelerates through the throat of the nozzle, and it becomes transonic. Here, where this yellow line, that corresponds to approximately Mach 1. The flow goes from a subsonic flow through transonic through a supersonic flow out of the exit of the nozzle. Of course, nozzles are designed to take high pressure and temperature fluids and accelerate them to create thrust. This is the whole job of the engine itself, and the nozzle is used to convert that energy into thrust. At the walls of the nozzle, we have set no-slip boundary conditions. Remember, that's where the flow velocity is set to zero, and we also specify something about the heat transfer rate to the wall, or solve it itself. It's probably a good idea to find heat transfer through a numerical method through a nozzle calculation. You can see the strange variation of the velocity magnitude near the wall here. It's a little bit discolored, and that's because there's a turbulent boundary layer there. You can see how tiny the turbulent boundary layer is relative to the rest of the fluid, which appears to be almost of uniform magnitude. But remember, it's not really uniform magnitude. It's just the colors are not fine enough to see. Anyway, at the inlet, we have specified a total temperature and total pressure. These are likely to be greater than a ratio of twice the ambient value of the ambient pressure. So you can see, using the basic no-slip boundary condition, a stagnation inlet set appropriately, and using the nozzle geometry and setting a supersonic outlet at the exit of the nozzle, because the flow is supersonic there, of course, we just can cut it off, and we extrapolate the information from the interior domain to the exterior to satisfy the supersonic condition, because all information is traveling downstream at greater than the speed of sound. We can do a simplified nozzle calculation. That's awesome. You might be wondering, and think back to your grid, our grid generation module. How would you distribute the computational grid within this particular nozzle? Certainly, you would have to have enough grid points to resolve the wall turbulent boundary layer. And you would have to have a lot of grid points near the nozzle throat, because capturing that transonic regime and its transition from subsonic flow to supersonic flow requires a lot of resolution. You probably wouldn't need a lot of resolution in the interior of the plenum of the nozzle, where my cursor is. Let's now turn to the so-called inlet and outlet mass flow rates. These are very popular in incompressible solvers, and a lot of students like them because, of course, you've learned volumetric methods originally in your classes. These might be where we simply set the mass flow rate at the inlet of the boundary and the exit of the boundary. If we only have one inlet and outlet of the domain, we would make sure to have our mass flow rates of the inlet and outlet to be equal. This can be enforced explicitly through some solvers, but usually as a user, you'll have to do this yourself. Now, you might have two outlets in your domain also. If you only have one mass flow inlet and two mass flow outlets, you would definitely have to make sure that the fractions of the outlets are equal to the total value of the mass flow rate at the inlet. If you don't, you would have an unbalanced mass flow rate in your system. However, if it's a steady problem and mass is increasing in your system and it's a compressible code, the mass flow rates can be actually unbalanced. And that way you'll have increasing density or decreasing density overall averaged in your computational domain. So if you have an incompressible solver, make sure that mass flow rates at the inlet and exit are indeed equal. So the wonderful thing about this, especially in the chemical engineering or petroleum industry, is we get to explicitly state and set the mass flow rates. It is unacceptable, for example, in the petroleum industry to lose track of oil quantities. Now you might be asking yourself, how can the velocities be determined, or other values of fluid dynamics? Well, of course, we would, in the practice of implementing these conditions, we would set mass flow rate. If it's incompressible, you would know density. You would also know the area of the faces. So using these simplified equations up here, where A is the area of the faces, m dot is mass flow rate, m dot sub f is the mass flow rate of a particular face, you could actually backtrack through the next equation, m dot equals rho AV essentially, dotted with v, remember it's the normal component of velocity for mass flow rate, you could find the corresponding velocities. This is all you're setting, and you would have to specify more variables according to the eigenvalue chart, depending if it's on an inlet or outlet mass flow rate condition. So typically, the temperature would be obtained through some sort of isentropic definition, given a total enthalpy at the boundary. That's one way to do it. The pressure could be extrapolated from the domain interior for the subsonic flows, and it would be specified for supersonic flows. So you can specify mass flow rate in these compressible flows. You'll just have to be very, very careful about the restrictions and boundary conditions. Of course, in contemporary solvers, this is all done automatic for you, but you should know this as a user so that you can diagnose problems, or if you're creating your own solver, you can explicitly code these things. Let's now talk about a particular outlet boundary condition, which is one of the most popular for compressible and incompressible solvers. It's very tempting for students to directly specify an outlet velocity or some mass flow velocity, but the pressure outlet boundary condition is one of the most robust conditions. As you imagine, it requires that you know the static pressure at a boundary of the flow and also know that the flow is leaving the domain there. That can be very difficult to do. Obviously, a static pressure outlet boundary condition, it could be supersonic or subsonic, will specify an area where it can exit the domain without affecting generally the internal solution. If recirculation, that is a vortice, goes through the outlet, it may corrupt the solution, or it could be stable. CFD solvers often have a little bit of different mechanisms to handle these situations, but hopefully it'll be stable for most situations. It's simply set by specifying the static pressure along with the boundary. For subsonic outflows, we would specify that static pressure at the boundary and let other values vary. For supersonic flows, we of course would only be extracting the values. So a static pressure outlet boundary condition can transition easily from a subsonic to supersonic flow. If the solver detects that the flow is supersonic, it'll only extrapolate the condition. If the flow is subsonic at the static pressure condition, it'll simply enforce the static pressure. So you can get into trouble with this condition where the boundary condition is fluctuating back and forth between subsonic and supersonic flows, e.g. the transonic condition. So you'll have to move your static pressure boundary condition far downstream from some object which is creating a transonic flow. This is critical, or else your solver will crash. Let's now look at a static pressure outlet condition. Here we see contours of velocity in the x direction. This is really a sharp bend, or a serpentine type structure, and there's an inflow condition here. It doesn't matter what it is for now. And there's an outflow condition here. This is where we specify the static pressure at the outlet. This is an unsteady simulation. The flow moves in and moves down this little bend. On the walls is, of course, a no-slip wall boundary condition. Simple. And we'll try an example like this in class. Next, let us look at one of the most popular boundary conditions in fluid dynamics for external aerodynamics problems. If you have an aircraft and you have a large computational domain around it, a free stream or so-called farfield boundary condition might be appropriate. This is simply enforcing the free stream velocity around the aircraft. The major equations are shown on the right. They're mostly self-explanatory. V is the velocity at the particular boundary. V infinity is what we would specify. Vf at some particular n is simply the velocity difference between the ambient and the current solution. A's, of course, are the particular areas. Now these are used for the boundaries that are far from bodies and contain small disturbances. So if you specify the so-called free stream or far-field boundary conditions, which are available in almost all excellent CFD solvers, especially in aerospace engineering, you have to make them very far away from the boundaries. For example, on the lower right, I've shown a cylinder in a cross-flow. This outer line is indeed where we would set the far-field boundary condition. The flow will seamlessly come in from the left if we set the flow to be, say, in the x direction with a particular velocity, and we'll go over the cylinder, which might be a no-slip or slip wall, and leave the domain behind the cylinder. You'll notice the distance from the cylinder to the exit to domain might be 10 or 15 cylinder distances. That's very small. For excellent calculations, I would recommend 50 to 100 cylinder diameters downstream. Why? Because the turbulent wake from the cylinder must dissipate and become relatively uniform before going through the far-field boundary condition in the exit. This is critical so that there's no reflections, and you can see this must be the case because of the simplicity of how we set the condition. These are set based on local flow velocities. For every time the solver makes a time step or iteration and solution, which we'll talk about later in the numerics section, we must detect if the current flow is into the domain or out of the domain. If it's a supersonic flow from in the domain, we simply calculate it from the specification. If it's an outflow, we extrapolate it. The harder part is if the flow is subsonic, going into the domain or out of the domain. Here, the so-called tangential components of the free stream velocity, which we've written as those bold A's over A magnitude, will be combined with the boundary normal velocity computed from the characteristics. So there is a method of characteristics calculation happening, which we talked about earlier. For pressure in supersonic inflows, the user would specify it. So you would typically specify an inlet Mach number or Mach number in the free stream and the ambient pressure. This is easy. So if our aircraft is flying at 1,000 feet, you might get the standard atmospheric pressure 1,000 feet. For supersonic flows, you wouldn't technically need to specify anything. The solver will take for it, but in practice you do. It'll just ignore your specification if it's a supersonic outflow. So for supersonic inflows, it'll use isentropic relations to find the so-called pressures and hold the Mach number constant at the far field or free stream inflow. At the outflow condition, it'll use an isentropic extrapolation to find those values. In the lower right, we have shown a figure of these type of characteristic calculations based on the particular outside or inside of the domain. For example, inside a domain would be the computational domain, and outside domain would be at the exit in this case. You can flip these values to find inlet conditions. Take a second to see these. You can imagine how they're derived using the method of characteristics using the flow equations of motion. This is usually done in a graduate computational fluid dynamics class. We would also be specifying temperature, and for supersonic inflows, of course, the static temperature would be specified. For outflows, it's extrapolated. And once again, for subsonic inflow and outflows, it would be found through the method of characteristics. Typically, for far-field boundary conditions, you only specify two things as a user: the Mach number and the static pressure, which would be just the atmospheric pressure for an external aerodynamics calculation, and simply place your free stream boundary condition very far away from the vehicle. Let's talk about one of the most robust and well-posed and physical boundary conditions. This is the so-called Riemann invariant boundary condition. This is very much similar to a free stream condition, but more physical and used for boundary conditions far from bodies. And it can also be used for inlet and outlet conditions for interior calculations, interior aerodynamic calculations. Now, the Riemann invariants are very much like the method of characteristics, that they correspond to the incoming and outgoing characteristic waves. We looked at the most basic example of the characteristic waves when we looked at the wave equation. We can't really do this for the full set of Navier-Stokes or Euler equations in this class because of time limitations, of course. Perhaps one day we'll make an additional video explaining this. Now, the invariants will determine the locally normal velocity component and the speed of sound. Here they're written down here in these equations. They are going to be dependent on the entropy S and the speed of sound C, which are used to determine the density and pressure on the boundary. So you can see the R plus and R minus for the positive, that is the incoming and outgoing characteristic waves, are written as some velocity plus or minus 2 times the speed of sound divided by the ratio of specific heat, Cp over Cv, minus 1. The other values and definitions are shown below. For example, speed of sound is gamma p over rho square root, and m is, of course, u over c. These are all local values on the boundary, so r plus and r minus change along the boundary, and they change as the solution develops. You can see the brilliance of this approach. It's based on the idea of these eigenvalues, which we showed earlier, and the characteristic lines. Here, these Riemann invariants mean that here at the boundary, we might have some velocity u, and it could be plus, where c is always positive, 2c over gamma minus 1. In the other case is 2c over gamma minus 1. So you can imagine that if u is very large, they might both be positive values. If u is less than, say, the velocity corresponding to the speed of sound, which would be about 340 meters per second for standard temperature, then, of course, we would have one positive and one negative r plus and r minus value. What does this correspond to? The information moving in or out of the flow. Now, if the flow is at the boundary and is locally supersonic leaving the domain, then there's no incoming characteristic waves, as I just explained, and r minus would be set to this value. If the flow is supersonic entering the domain, then no outgoing waves exist, and r plus would be set to this value. So you can see in these two cases, we actually modify slightly r plus and r minus, depending on the condition at the wall. It's very minor, and they're not really changing the values. This is really happening automatically. Now, of course, the velocity and the speed of sound at the boundary are, of course, the sum and difference of the invariants. This is an amazing and wonderful property and part of the popularity of the condition. So, for example, the velocity would be the summation of the two Riemann invariants, and the speed of sound would be the difference. These can be derived from the previous equations. Now, we impose a velocity on the boundary, and it will depend on the local flow direction. So if u is positive, then the flow will exit the computational domain. The entropy is extrapolated, and the interior is used to update the density at the boundary. Obviously, the opposite happens for a negative value u. That means the flow is entering the computational domain, and the free stream entropy would be used, which could be derived from the free stream temperature in some cases. Let's summarize these conditions here on this slide. You're welcome to read through this yourself. Let's look at an example of the application of the Riemann invariant boundary condition. This is a particular flow where we see contours of the solution and the flow is moving left to right. You might see the carbon vortex street in this higher speed flow. You can see the cylinder shedding. It's really beautiful. Now, the domain is very small around the cylinder. You may not be able to get away with this with the farfield boundary condition. Notice that the cylinder diameter is about the 2 widths of my cursor, and it's maybe 10 to 15 down, the exit boundary condition is maybe 10 to 15 boundaries downstream. The walls that are in the streamwise direction are very, very close to the cylinder too. So disturbances of this turbulent wake are going through the Riemann invariant boundary condition at the exit of the domain and the sides. The front of the flow has very little disturbances. But you can see, because the Riemann invariant boundary condition is very much based on these characteristics, that it's able to flip back and forth very efficiently between the supersonic and subsonic type flows or very large vortical structures coming through the exit of the domain. Remember, a vortice going through an exit of the domain at lower speeds, like in this case, might cause inflows to occur at the exit of the domain. Now, your static pressure outlet will not normally be able to handle that, and it would crash. Your free field or far field boundary conditions do not handle large disturbances near the boundary either. So your best choice in this case, where you're forced to have a smaller domain, is a so-called Riemann invariant invariant boundary condition. Your best choice would be to make the domain even bigger and have the Riemann invariant boundary condition. Of course, there's even a slightly smaller computational expense, but it's not that huge, and it's definitely worth it because it helps eliminate reflections. These Riemann invariant boundary conditions can also be used in interior flows. Let's now talk about a specialized boundary condition. If there's very strong turbulent structures or nonlinear waves or shock waves exiting the domain, it might be required that we use the so-called absorbing or sponge layer boundary condition. This is just a wonderful word because it's very physical and it describes what's happening. A sponge absorbs something. In this case, it is absorbing the disturbances leaving the domain and allowing the flow to move through it easily. This is very much like a porous material. Like if you put water through a porous sponge, it would flow through at a slower rate a little bit, but it would also completely damp out any disturbances. This is a good way to remember it. Just think of it as like a sponge layer or an absorbing layer. Now, a sponge layer is typically a region where we are damping the flow of values about a mean value. I've shown one set of example equations here of a simple sponge layer formulation. Let's just describe it from a overhead view. Up here we have a vector set of the equations of motion. We've shown one vector set of equations earlier in this module. Now, the damping might go as something like S. Now, Q is the variable which we're trying to damp. This little sigma is the damping parameter, which is a function of space. Now, sigma will vary from 0 to 1 smoothly. Its definition is down here. Don't worry about this form right now. This is a form written for a full three-dimensional solver. On the right, you can see that the damping of the coefficient with time will be a value between 0 and 1 of, say, the density minus the ambient density, the momentum terms minus the ambient momentum terms, and the energy minus the ambient momentum. So as a disturbance moves through a sponge layer, which are written around the edges of the domain, which we'll show an example of in a second, it will lower through damping the solution from its value towards the ambient value. Now, sigma varies from 0 to 1 from the interior of the sponge to the exterior of the sponge. Let's look at this graphically. Here's one example of a sponge layer calculation. It's a two-dimensional simulation, and as a function of time. These are pressure contours. So the higher the contours and color, the higher the disturbance. The green contour is the ambient. If we are disturbing the fluid at one particular point, and you can see that this is a subsonic flow with ambient, with a Mach number of 0 essentially, so the eigenvalues correspond to acoustic waves going in all directions equal, the positive speed of sound and negative speed of sound direction. You can see that initial disturbance creates a wave. With time, the wave spreads out from the initial disturbance from A, B, C, D, E, F, G, H, I, and it goes out more and more. Now, this part of the domain in I is far away. This part of the wave is moving in the upper left direction and hasn't hit the boundary yet. Now, from the middle disturbance, where my cursor is now, to the lower right, you can see that the disturbance has left the domain. It hasn't reflected off the wall. There's a minimal reflection you can see in particular case F. What's very interesting about this is these waves approach the wall, they're damped or absorbed. Now, the actual computational domain we're finding the solution is the interior points. The exterior points around the boundary, a set of them, have values of sigma from 0 to 1. Values of sigma at the actual boundary itself are set to 1, and values of sigma a few grid points in the interior are set to 0. They're allowed to vary from 0 to 0.1 to 0.2, etc., all the way up to 1. So as the solution advances through the sponge layer of the boundary, it's actually being damped. That's a brilliant idea. The problem is sometimes it causes reflections, like in case F, from the three initial disturbances, which are the same. Another important boundary condition which you should absolutely be aware of and take advantage of, especially in steady simulations, is the so-called symmetry condition. The symmetry condition is actually equivalent to the no-slip condition. They are exactly the same, but they're just implemented a little bit differently in the codes. Now, the symmetry condition physically states that there's no flux or velocity through the boundary, and that all the partial derivatives of the field variables are equal to 0 across the boundaries. There's no scalar flux across the boundaries, for example, like some temperature flux or something. That's what I mean by the partial derivatives. To implement this, we simply set the velocity tangential to the boundary to 0, and we let the velocity parallel to the boundary vary. The normal derivatives are set to 0. Alternatively, you can also enforce this by setting the shear stress to 0. So this would be a case where we set a plane or line in 2 dimensions within our computational domain boundary condition to mirror the solution about the symmetry plane. I talked about the symmetry condition earlier in the class, and it could reduce computational expense greatly. There's also such a thing as an axisymmetric boundary condition. If you have an axis of symmetry in 3 dimensions, you can do a 2-dimensional simulation instead of a 3-dimensional simulation by enforcing the axisymmetric boundary condition. This just means that the simulation can be rotated on a plane around its axis to produce a full 3-dimensional simulation. This is often used in, say, a circular nozzle calculation. Or perhaps there's an aerodynamic body which is symmetric around its axis. That means it has infinite number of planes of symmetry around a single axis. This is a very powerful boundary condition because it takes a 3-dimensional simulation and creates a 2-dimensional solution, which is equivalent. That's a huge computational savings. The symmetry will cut down your number of grid points typically in half if there's a single plane of symmetry. Let's look at one example of a great candidate. Here's a CFD simulation. It's probably compressible. The flow is left to right of the NACA 0012 airfoil. You'll notice that the contours of the solution, and it doesn't matter what the variable is in this case, are particularly symmetric. You can imagine that I take a mirror and place it across the screen, and I could look in the mirror from the bottom or top and see the same set of data mirrored across the plane of symmetry. So here the plane of symmetry is where my mouse cursor is moving, which is probably through the x-axis. I could apply a symmetry boundary condition to the simulation by simply cutting the grid through the middle and ending it at the leading edge and keeping it along the top edge and having another cut through the back plane. So you can imagine you can put your hands over the bottom part of this page and only solve the upper part of the domain. You've cut your number of grid points in half by applying the symmetry condition, because you know in advance for a steady statistically stationary solution that you'll have a symmetric solution. And we'll talk about this in our class and try some examples. Let's look at another important condition. This is the so-called periodic boundary condition. This is not necessarily required, but can create extensive computational savings. I've discussed the idea of the periodic boundary conditions previously. Let's look at it mathematically. For example, in one case, for scalars or velocities, you might simply set, if velocities are w and scalars are phi, one value at one end of the domain equal to the other, and vice versa, the other end of the domain equal to the opposite. That sounds very confusing. Let's look at a particular example. For example, I have a little burner here. A very simple one. And you can see that there's actually planes of symmetry in a sense. However, the flow may be 3-dimensional and not exhibit those planes. For example, the flow might enter this dashed line here and go around. It's swirling in the burner. So you may not easily be able to set multiple planes of symmetry. What we could do is take a cut of the domain at some angle from this dashed line to the next, which would be some value of theta. The flow would enter the domain and exit the domain correspondingly at these dashed lines. Those are the planes where we put a periodic boundary condition. Like I said before, if something enters the right domain, it would leave the left, and if something enters the left domain, it would enter the right at a corresponding position across the x equals constant line in this case. So in this case, we might be able to reduce our computational domain size by a factor of, well, let's see. We have 1, 2, 3, 4, 5, 6. So that would be 1/6 the computational domain size by using periodic boundary conditions. You'll have to try this out for yourself to see some examples. You can also do this in perhaps swirling flows. You'll have to be careful what assumptions periodicity means. For example, in the flow burner, you'll have to assume that we are capturing all the large-scale structures of turbulence within the burner, and they can be captured with this periodic domain. It's very unlikely that is not the case in actual burners. Finally, we'll talk about the immersed boundary condition. This is where we do not necessarily set a wall boundary condition. Instead of enforcing the velocity equal to 0 at the wall explicitly, we would simply add in a source to the right-hand side of the momentum and energy equations. So for this case in the lower right, the blue line would represent where we want a wall. The points here are grid points. The points on this side of the wall, we would want to represent a solid surface. The points on the outside of the wall, of course, are a fluid. These points are generally the same set of equations we would be solving typically. Now, on the solid surface of the wall, we would have these grid points and equations of motion. For these particular equations, we would be adding sources of momentum and energy to the equations of motion to balance the forces and energies on the other side of the wall so that no flux can go through this particular line. This is the so-called immersed boundary condition. This is a very, very difficult boundary condition to implement because now we are solving the same fluid dynamics equations with a modification of inhomogeneous sources along these lines of the wall. And we will have to use the computational power of the solver to find solutions inside the wall and outside. At the end, when we visualize the results and examine them, we would disregard the solid wall grid points. They're only there to enforce no flow through the wall. You can imagine there's a major advantage of this approach. We can just use structured grids and not ever worry about resolving the geometry of the vehicle. We would only need to impose through mathematics in the solver equal and opposite forces and energies within the equations of motion. The disadvantage, of course, is it is computationally expensive, and you'll never exactly resolve the very complicated shape of the boundary, which you might be able to do with explicitly setting grid points and velocities to 0 at the wall. But you can see it completely removes the difficulty of the grid generation problem, which we talked about earlier, and consumes the majority of the user's time. Next time, we're going to be talking about these particular boundary conditions and many examples. We'll be talking about their best placement, their best use for all kinds of types of problems: external flows, boundary layers, jets, pipes, Couette flows, and more. And most importantly, we'll be talking about their placement. A misplaced boundary condition can lead to a solution which is unphysical or divergent. Thank you very much for your time today. I'm Professor Steve Miller.